Okay, so it's my pleasure to introduce Diganta Borah from ISER Pune. Diganta was a student at IISc, I mean, a few years ago. He was Kaushal's student, and I see Kaushal isn't here, but at least Gautam is. So Diganta will talk about limits of an increasing sequence of complex manifolds. So over to you, Diganta.
Thanks, Vamsi. And I also thank the organizers for giving an opportunity to talk here. Okay, so the title of the talk is Limits of an Increasing Sequence of Complex Manifolds, and it's joint work with G.P. Balakumar, Rachi Mahajan, and Kaushal Verma. So, okay, so let me begin by describing the problem that we are interested in. So suppose we have a complex manifold M, which is the union of an increasing sequence of open subsets Mj, each of which is biholomorphic to some fixed domain omega in Cn. Then it is of interest to describe M in terms of this fixed domain omega. So we'll refer to this problem as the union problem. And this is what we are going to talk about today. So let me first give you some background on this problem. So the origin of this union problem actually lies in the solution of the Levy problem, where an important step is a result by Wittgenstein that states the union of an increasing sequence of domains of holomorphy is a domain of holomorphy. Now, see, domains of holomorphy are precisely the Stein manifolds in Euclidean spaces. So necessarily a question arises whether this Wittgenstein's result holds for general Stein manifolds also. But Fornaess actually came up with a counterexample, first in dimension 3 and then dimension 2. So basically, in other words, there are, complex manifolds which are exhausted by Stein manifolds, but the limit, that is the union, is not Stein. Okay, but as a next step, then one can ask, suppose each of these exhausting domains, each Mj has some extra condition. So how does that affect the limit, that is the union M? So for example, we can ask whether, say, if each Mj is biholomorphic to omega, some domain omega, so is M also biholomorphic to omega, or can we describe at least M in terms of some properties of omega? So that is the union problem. So in other words, the union problem is just an offshoot of this solution of the Levy problem. Now let me describe some simplest cases of the union problem. The simplest case is when you take this fixed domain omega to be the unit polydisk or the unit ball. Okay, so this was studied by Fornaess and Stout. They showed that if we assume an extra condition on the limit domain M, namely not domain, so the manifold M, namely if it is a taut manifold, or more generally an open subset of a taut manifold, then M happens to be biholomorphic to omega. So this result, you see, immediately implies that we cannot exhaust the unit ball by the unit polydisk, or the unit polydisk by the unit ball, because they will be otherwise biholomorphic. Right? Okay, so since they're mixed audiences, so it would be good to recall a few elementary definitions which we are going to use throughout the talk. So by a taut manifold, I mean a complex manifold such that any family of holomorphic maps from the unit disk to M is normal. That is, you take any sequence of holomorphic maps from the unit disk to M, then it has a subsequence which either converges uniformly on complex subsets of delta, or diverges uniformly on complex. Also, the Kobayashi pseudometric of a complex manifold M is defined as follows. It is the function, it's a non-negative function on the tangent bundle Tm. So tangent bundle here, I mean the complex tangent bundle. So this is defined by infimum of 1 upon R, such that R is positive. And there is a holomorphic map from the unit disk to M that takes 0 to P, with f prime at 0. So this is f prime at 0 is the derivative of f at 0 applied to 1. So this is r times v. So this can be thought of as a measure of the largest disk that fits inside M at the point P in the direction of the vector V. Okay, so larger the metric, smaller will be the disk. Also, if we integrate this Kobayashi pseudo metric, then we actually get a pseudo distance on M, then which is called the Kobayashi pseudo distance. And if this pseudo distance is a true distance, then M is said to be Kobayashi hyperbolic. And if Kobayashi distance is complete, then M is called the complete hyperbolic manifold. All right, so let me talk about some more known results. So Fornaess and Sibony solved the union problem using the Kobayashi metric. So let me describe the result. So assume that omega mod odd omega is compact. Okay, and consider the following two cases. When M is hyperbolic, so I'll refer to this as hyperbolic case when the limit is hyperbolic. So then they showed that M actually is biholomorphic to the fixed domain omega. And if M is not Kobayashi hyperbolic, so I'll refer to this case as non-hyperbolic case. Then they showed that look at the zero set of the Kobayashi metric at some point P. This is a complex subspace of the complex tangent space. And so this they showed that this is dimension of this space is actually independent of P. Further, so I will call this as the Kobayashi. So this dimension, the constant dimension, will be referred to as Kobayashi corank of M. And if this corank happens to be 1, they show that there is a holomorphic retract Z of omega, such that M is biholomorphic to a locally trivial fiber bundle over Z with fiber biholomorphic to C. So then variance generalize this result to omega being strongly pseudo-convex. So they got rid of this assumption that omega has a compact quotient under action of odd omega. So for strongly pseudo-convex domain, they showed that in the hyperbolic case, the limit is biholomorphic to either omega or to the unit ball. And in the non-hyperbolic case, they have the same conclusion as that of Fornaess and Sibony. Okay, so this is the background on this problem. Now let me state our result. Problem that is M is exhaustion of increasing exhaustion of M is exhausted by biholomorphic measures of some domain omega. So we are in the hyperbolic case, that is M is assumed to be hyperbolic. And again, we want to remove the assumption that omega has a compact quotient under the action of odd omega. So here are various class of domains that we consider. So first, suppose omega is bounded Levy-Coring 1 domain, by which I mean that so it is a smoothly bounded domain, smoothly bounded pseudo-convex finite type domain. And the Levy form of the boundary has, so it is because of pseudo-convexity, it says now all the eigenvalues are non-negative. So what I want is that at the most one eigenvalue is allowed to be 0. Okay, so in other words, so strongly pseudo-convex domains for which all the eigenvalues are positive, they are Levy-Coring 1 domains. Or if we are in C2, then so any pseudo-convex finite type domain is actually Levy-Coring 1 domain because of dimension argument. All right. So in this case, what we can show is that the limit M is biholomorphic either to omega or a domain of the following form. So omega infinity, this consists of all Z in Cn such that 2 times real part of Zn plus a subharmonic polynomial without any harmonic terms plus summation mod of Z square, Z from 2 to n minus 1 less than 0. So this domains omega infinity basically arises from, we'll see shortly, it arises from scaling of Levy-Coring 1 domains. Okay, so next we consider convex finite type and convex infinite type domains. So both are by boundaries are so smooth. So we have 2 categories: convex finite type and convex infinite type. So for these domains also scaling principle is available, and in this case also we can show that the limit is biholomorphic either to omega or a limiting domain. Okay, let's go to case 3. So we'll stick to C2 in this case, and let omega be a strongly pseudo-convex polyhedral domain. This means that omega is intersection of finitely many smoothly bounded domains, such that so two properties should be satisfied. So whenever two or more boundaries intersect, they intersect transversely. And second, smooth boundary points should be strongly pseudo-convex. So these domains also can be scaled. And in this case also, we have the limit is either biholomorphic to omega or a limit domain arising from scaling. Some more cases to consider. So let's take omega to be the following domain. This is called the minimal ball, which is actually the unit ball in this norm, defined by square root of the quantity that I have highlighted. So this is half of the Euclidean norm square plus there is an extra term, summation z from 1 to n zz square. So this turns out to be a norm, and then the unit ball in this norm is called the minimal ball. So in this case also, so here we need an extra assumption on M. So we a priori need to assume that M is complete. Okay, then we can show that M is actually biholomorphic to omega. So this domains also has scaling, and then what is good in this case is that the limiting domain that you get from scaling actually is biholomorphic to the original domain omega itself. That's why we don't have the dichotomy here. Okay, so M is just biholomorphic to omega because omega infinity itself is biholomorphic to omega in this case. Okay, next we consider again in C2. Suppose omega is a simply connected domain with generic piecewise smooth Levi-flat boundary, by which I mean that again omega is intersection of finitely many smoothly bounded domains, such that whenever two boundaries intersect, they intersect transversely, and all the smooth boundary points should be Levi-flat. That is, Levi forms should have 0 eigenvalues there. So then in this case, M it turns out to be biholomorphic either to omega or to the unit by this delta 2. So finally, the final case is when omega is, we assume that omega is a symmetrized polydisk. We also need to work with domains in Cn rather than general complex manifold. So we take omega to be a bounded domain in Cn. Then in this case, we find that omega is biholomorphic either to omega or there is a proper holomorphic correspondence from M to the unit polydisk. Okay, so this is the result in the hyperbolic case. We also have the result in non-hyperbolic case, but first let me give you a sketch of the proof of this result. So let's recall the setup. So we have the exertion of M by Mz, and each Mz is biholomorphic to omega. So let's call this biholomorphism Cj. Now let's fix a point Z0. Then Z0 is in Mz for all large Z, but without loss of generality, we'll assume that Z0 is in Mz for all Z. Okay, and let's consider the image of this point under the biholomorphism. So let's call it by Pz. Okay, so Pz is Cj of Z0. So we'll call this orbit under Cj, orbit of Z0 under Cj. So there are two cases to be considered. One is when Pz is relatively compact subset of omega. Then omega is let's all right. So I should have mentioned that all the cases that we have considered, all the classes of domains that we have considered. So these domains, the fixed domain omega in these cases are always thought. Okay, so this allows us to, this gives us actually a limit of this sequence Cj. And because M is assumed to be hyperbolic, standard arguments can be used to show that C turns out to be biholomorphic. So I'll not go into the detail of this case. So interesting case is when, Pz accumulates at the boundary, this orbit accumulates at the boundary of omega. So I'll assume that Pz itself converges to some boundary point P0. And first, let's consider the cases, 1 to 4. Recall, so 1 is Levi-Corank 1 case, 2 is convex finite and infinite tape case, 3 is the minimal ball, I hope so. Let me recall this. So, oh no, 4 is the minimal ball and 3 is strongly pseudo-convex polyhedral domain. Okay. So the reason I am collecting all this together is that the scaling is available in all the cases. Okay. So so I don't want to describe the scaling method here because I won't have time for this. But what it gives us is the following. So it gives us a sequence of maps AZ, biholomorphisms actually, AZ from omega to omega z, such that this domains omega z converges to some domain omega infinity in the local Hausdorff sense. And the image of the orbit, so let's call it qz. Okay, AZ of pz is denoted by qz. They converges to some interior point in the limiting domain omega infinity. Okay, now let's consider the following composition. So we have this biholomorphism Cj from mz to omega. So these are the initial biholomorphism that we started with. Now we also have the scaling map, so we compose them. Okay, so let's call this composition Az o Cj by Cj tilde. Okay, and it should be observed that Cj takes this point Z0. So remember, Z0 is by under Cj goes to Pz, and Az takes Pz to Qz, and we have we have that Qz converges to some Q0, right? So we have all these facts. Plus, it is also known that the limiting domain arising from scaling in all these cases is actually taught. Okay, the limiting domain omega infinity is also taught. So this because of this, the sequence of maps Cz tilde, these compositions, they have a limit, and let's call them.
Diganta, may I interrupt for a second?
Yes, sir.
I'm a bit confused with your notation. Could you just go back to the previous slide? PJs are the images of a fixed Z under the psi chase, right?
Yes, yes.
And in case 2, you are saying this has a limit point P0. Sorry. So there's a typo, yes?
This should be Cz tilde, yeah. Okay, sorry, thanks. This one, right?
Yes.
This is the Cz tilde, yeah. Thanks for pointing it.
Thank you.
Okay, so this gives us a limit of this composition. Let's call it by C tilde. So this is a map from M to omega infinity. So this is the first step. Next step, we show that this map is actually biholomorphism. Now note that C tilde, this is actually, so let's go back to the previous picture. So C tilde is, you see, is the limit of this Cz tilde, and Cz tildes are biholomorphism. So now we are looking for an inverse of C tilde. So a natural candidate would be to look at the inverse biholomorphism Cz tilde inverse and try to find a limit. But the difficulty is that, so they are maps from omega z to mz and hence to m. But m is not a priori known to be taught. We don't have any condition on m like that. So the existence of such a limit is not clear. So we need an intermediate step, which is the following. So we use the stability property of the Kobayashi. D here is Kobayashi pseudo distance. So it is one can show that they are actually stable under scaling. So in the sense that, so if you look at the Kobayashi pseudo distance of omega z, so their limit is not more than the Kobayashi pseudo distance of the limiting domain. Okay, so using this fact, we can actually show that the map C tilde is injective. Okay, but once we know that C tilde is injective, so M is now biholomorphic to C tilde of M, which is inside omega infinity, and omega infinity is taut. So in other words, we can actually regard M as a submanifold of a taut manifold, and that helps us to get a limit of this inverse maps that I said. Okay, and let's denote this limit by phi tilde, and then one can, with standard arguments, one can actually show that the phi tilde itself is the inverse of the C tilde. Infinity. Okay, so the cases where scaling is available is, so am I audible and visible? My internet connection seems to be interrupted. Am I audible?
You are visible and audible to me, at least. I don't know about the others.
Okay, it's fine. Yeah, thanks. Okay, the cases where the fixed domain can be scaled are done. So what is left are the following two cases. One is when omega is, so it has generic piecewise smooth boundary, Levi-flat boundary. So scaling is not available, but Fu and Wong actually studied some Wong-Rosset type result for such domains using the C by K invariant. So, and using their work, we can actually establish the following. So here C denotes the Kobayashi Eisenman volume element, and K denotes the C denotes the Karatari Eisenman volume element, K denotes the Kobayashi Eisenman volume element. So using their arguments, what we can actually show is that, so if you look at this CMZ by KM, at the point Z0 is greater or equal to 1 for all Z. But remember, MZ is an exhaustion of M, so they're increasing and a limit is same. So one can actually show that the Karatari volume elements converges to that of the Karatari volume element of M. So in the limit, we have this Kobayashi by this C by K invariant for M at the point Z0 is greater or equal to 1. But this invariant is always less equal to 1, which actually is a conjugate of the Schwarz lemma. So in other words, this invariant is equal to 1 at the point Z0. I should have mentioned that here we are actually, though I have written, I didn't mention. So we are the C by K invariant we are considering is with respect to the polydisk. Usually it is defined with respect to the ball, but nevertheless we can define it with respect to the polydisk also. So, now it is known that if this invariant is 1 at some point, then the domain, so the manifold has to be identically equal to the domain with respect to which this invariant is defined. So M turns out to be biholomorphic to delta 2. Okay, so the final case where omega is actually assumed to be the symmetrized polydisk. So in this case, what we do, so let's denote by pi the symmetrization map, and let's pick any point. So in the the inverse image of the orbit, okay, under pi. We can pick anything; it doesn't matter. Now let's look at the following composition. So we have this. So the CZ where's the initial biholomorphisms. So these are from MZ to now the omega is symmetrized by disk. Symmetrized polydisk. In other words, we can view CZ as a holomorphic correspondence by simply composing with with pi inverse. So CZ, so pi inverse of CZ is a holomorphic correspondence from MZ to delta n. Okay. Also, we choose a map HJ. This is an automorphism of delta n, which takes this lambda z to the point 0. So this composition, which is a holomorphic correspondence, note that because of our choice of HJ, we have so this holomorphic correspondences take the point. Okay, so here we can actually use a result of Klinzenberg and Pinchuk, which tells us that this family of correspondence or holomorphic correspondence, this is a proper holomorphic correspondence. This family is actually normal, hence has a limit. And this limit is also a proper holomorphic correspondence from M to delta n. So this takes care of the final case also. Okay, so this is the so this is the result in the hyperbolic case. So let me. So how much time I have?
Actually, yeah, you have around 5 minutes or so.
Okay, I'll try to go quickly. Try to finish.
No problem. You can go. That's
yes,
fine.
yeah. Okay, fine. Yeah. So let me just go to the next case. So non-hyperbolic case. So assume that M is a non-hyperbolic manifold, and suppose omega is as in case 1 to 3 of theorem 1. So remember, 1 is the Levi-Korank 1 case, 2 is convex finite and infinite case, and 3 is the strongly pseudo-convex polyhedral case. Okay, so if omega is one of this, and then we can actually show that the conclusion of Fornaess and Sibony holds in this case also, in the sense that, so if you look at this zero set of the Kobayashi metric, this is the dimension of this is independent of P, And if M has corank 1, then M is biholomorphic to a locally trivial holomorphic fiber bundle over a retract Z of omega, or a retract Z of omega infinity. Again, we have the dichotomy which arises because of scaling. Okay, so let me give a so the proof actually, the proof of this is the arguments are similar to what Fornaess and Sibony did, except that we need to point out how the retract Z is considered. So I'll just basically outline how the retract is considered or constructed. So let's recall the notations we already have. So we have this initial biholomorphism Cj and the orbit Pj. So we again have two cases to consider when Pj is this orbit is actually a compact subset of omega. So in this case, the arguments of Fornaess-Sibony goes through, so we don't have to do much. So again, interesting cases when Pj accumulates at some boundary points, and assume that Pj itself converges to P0. So in other words, we have again the scaling method available to us. So I again borrow the notations from the previous proof. So let's first consider the following composition. So this initial biholomorphism Cj and the scaling maps Aj. So let's we denotate it by Cj tilde, and we already know that because omega infinity is thought, so we have a limit C tilde from M to omega infinity. Now let's consider the following composition. So omega set to mz, so we have this inverse of this initial biholomorphisms, and then mz to omega infinity, we consider this map C tilde. Remember, mz is sitting inside M. So we can look at this composition. Okay, let's call it, say, alpha z tilde. And because again, using the fact that omega infinity is thought, one can actually get a limit of this sequence of maps. So let's call it alpha tilde. And one can also check that alpha tilde actually fixes the images of C tilde. Okay, so alpha tilde of C tilde Z is the C tilde Z. So then we define Z to be all those points in omega infinity which are fixed by alpha tilde. So this certainly contains C tilde of M, as we just observed. But one can actually check the following, that Z tilde is equal to C tilde of M. Okay. And Z tilde is a closed connected submanifold of omega infinity. And the map alpha tilde is actually retraction from omega infinity to Z tilde. So in other words, Z tilde is actually retract. Okay. One can also check that this C tilde has constant rank. All right. Now, see, C tilde Z's are biholomorphisms, right? So, in our other words, Kobayashi isometry. So we have f of the Kobayashi metric of mz is same as Kobayashi metric of omega z under this CZ tilde maps. So, but Kobayashi pseudometrics are stable under scaling. So this gives us that the Kobayashi metric of M is equal to Kobayashi metric of omega infinity under C tilde. Okay, so C tilde actually preserves the Kobayashi pseudometry. But you see, omega to infinity is a hyperbolic domain. So this means that the left-hand side is 0. So this is 0, if and only if right-hand side is 0, which is true if and only if derivative of C tilde be applied to V is 0. So in other words, 0 set of the Kobayashi metric coincide with the kernel of the this linear map derivative of C tilde at P. But we already mentioned that C tilde has constant rank. So this means the derivative of C tilde has constant nullity. So dimension of the space, the 0 set is constant. All right, so this is fine. Then once you assume that the corank is actually 1, then the rest of the arguments, as I said, is same as Fornaess and Sibony. So I don't want to, they're quite involved. So let me not go into the detail of that. So, but this takes care of the case in the non-hyperbolic case also. Okay, some quick corollaries. So the first one is, suppose we have a smooth, strongly pseudo-convex domain in Cn. Then one cannot exhaust it by symmetrized polarities. This is because, you see, so there are two cases to consider. So it's strongly pseudo-convex domain. So our theorem 1 applies in this case. So D would be either biholomorphic to the symmetrized polarities, or okay. So so if you, so this is theorem 1, the last case actually we are applying, or it will be so there will be proper holomorphic correspondence from D to the symmetrized polydisc. None of this is possible, so it follows the corollary. The second corollary is, so suppose and next domain. Okay, then if M is biholomorphic to omega, M is hyperbolic, then M is this is immediate consequence of theorem 1. And in the non-hyperbolic case, we can describe M more explicitly. We can actually say that M is biholomorphic to delta cross C. Okay, and the proof goes like this. So in the non-hyperbolic case, you see, so we are in C2 and we are working with omega is a strongly convex domain. So thanks to Lampert's work, in this case, Z is of the form image of some Kobayashi extremal. But again, by Lampert's work, Kobayashi extremals, they are actually complex 0 to 6. So F is actually an embedding. So this means that Z is actually biholomorphic to delta. So in other words, both the Z admits solutions to both the cosine problems. And this fact can be used to actually show that M is biholomorphic to all of Z cross C. Okay. So this takes care of this corollary. Now, the final result, I will probably only state this. See, theorem, because of theorem 2, it is of interest to understand retracts of domains in Cn, right? Because this would allow us to describe the limit more explicitly. So retracts of polydiscs and balls are known. But retracts of polydiscs times balls were not known. So this is our result. So let's take omega to be, say, a disk cross Bn, and Z is a retract of delta cross Bn, and suppose that Z contains the origin. This is a minor assumption because the automorphism group of delta cross Bn acts transitively, so we can assume Z actually contains origin. Okay, and assume that Z is not trivial. Then we have a complete description of Z. So here are the cases. So one of the cases that Z is a graph of some Bn valued holomorphic mapping of the unit disk, or Z is the graph of some disk valued holomorphic function over a complex linear subspace of Bn. And finally, Z is the intersection of a linear subspace with delta cross Bn of complex dimension at least 2. So this is exhaustive. All the cases, these are all retracts are of any of this form. Okay, so I won't have time to go into detail, but just I'll just outline. I'll briefly say how one attacks this. So the idea is to actually examine how the tangent space to Z at the point Z0 intersects the boundary of the domain delta cross Bn. For example, so this simplest case you consider. So suppose this tangent space intersection, the boundary is contained in the distinguished boundary delta of delta cross delta of Bn. Okay, so for simplicity, let's call this intersection of the tangent space with delta cross Bn to be L. Okay, so we are in the case when the boundary of L is contained in the boundary of delta cross boundary of Bn. So because of this, so if you look at the projection into the first factor, it is actually a proper map. But proper holomorphic maps do not decrease dimension. So it follows the dimension of L, hence dimension of L is actually 1, dimension of Z is 1. Also, see, pi1 is linear, so therefore the fibers of pi1 are the singletons. And hence pi1 itself, pi1 is actually a biholomorphism from L to delta. So in other words, so if you look at the inverse of pi1, so that actually parameterizes L. So L has to be of this form. Okay, so W comma some beta is of W, and beta is our linear. L is linear, right? So then one actually with some more arguments so that itself is equal to Z. Okay, so the rest of the cases are also similar, though they are different, but they can be proved similarly. All right, so I think I'll stop here. And thank you.
Right, let's thank the speaker. Right. Thank you, Diganta, for the nice talk. Are there any questions?
Yeah, Diganta, I had a question about the first theorem. you made some remarks about needing some additional hypothesis. I wonder if that is even needed. Now, first of all, isn't the minimal ball already Kobayashi? It's known to be Kobayashi complete, right?
The minimal ball, yes, yes.
So,
but to work, see, I am the additional assumption on M. So finally, of course, we are going to show that M is biholomorphic to omega, but to work it out, we actually need to assume that M is complete.
Okay, so now, so somehow I didn't observe the role, since there was a unified argument for cases 1 through 4.
So here, basically,
where exactly was completeness of M coming into the picture?
To show the, when we look at the scaling maps, and then we compose CJ with the scaling maps. And we need certain normality argument there. We need to establish that they are normal. So if we do not assume M to be complete, so the proof, we believe it can be done, but then the proof actually, as of now, we have doesn't go through. So that's why we assume that M is complete.
And then
I think so more precisely to show the Hausdorff convergence. Yeah, I remember now. So to show that the Hausdorff convergence of the domains, we actually need to assume that M is complete.
I see. And could I have a look at parts 1, 2, and 3 again, please, then?
Yeah, yeah. So here everything goes through nicely, but the scaling, when we do for the minimal ball, so this basically this was by Kim, but why so?
Oh, okay, I get it. Right. No, I get it now. I suppose what you are. Let's see. Yeah, okay, sorry, my mistake. Carry on, I interrupted.
Yes, yes. Yeah, no, that's it. So, yeah.
So why is it that one doesn't explicitly need to add the assumption on completeness for 1, 2, and 3?
So as I see it here, we want to establish that the scale domains converges to some limiting domain, local Hausdorff sense. That is, in this case, it goes through very well. But so for the minimal ball, so of course we are following Kim, but the proof, when we try to write down in this case, so we realize that it doesn't go through under without the assumption that M is actually complete.
Okay, got you. Thank you.
Yeah.
Any other questions? All right, if not, let's thank the speaker again. All right, so we'll end the session for now. We'll break for lunch, and we'll resume at 2 again.